Multinomial regression models provide us another way that we can examine association in a contingency table structure. To see how this is done, what we can do is go back to our situation where we had y as our column variable, x as our row variable, and for our row variable x, we can include that as the explanatory variable in a multinomial regression model by simply forming I-1 indicator variables to represent this I-level categorical variable. Now, with respect to our column variable y, well, we treat that as our response variable, where it has probabilities of being in one of the categories of pi 1, pi 2, all the way up to pi sub capital J. So with that then, here's what our multinomial regression model would be for a I by J contingency table. So on the left side, I should say, we have this log of the odds for category J versus category 1 relative to the Y response variable. And then on the right side, we have our normal structure of this linear combination of the regression parameters with the explanatory variable values. In this case, explanatory variables are actually represented as indicator variables. Now, in here, I do one little small change. Notice how I start with an index of 2 for these indicator variables rather than 1. Simply, the reason why I did it in this particular scenario is because remember how R treats categorical explanatory variables. It sets the first level equal to 0 when forming the indicator variables. So this x of 2 here then essentially is the indicator variable corresponding to row 2 of our contingency table. And then I changed the beta subscript to match it. 1 does not have to do that, but that's what I did. And so notice how we go up to capital I for these indexes. So now a model under independence with this kind of a setting is simply a model that doesn't have x in it. Why? Well, think about what independence means in a contingency table structure. How the responses for our column variable come about are not affected at all by how the responses for the x variable come about. So in other words, then we should remove all the x's then from our corresponding multinomial regression model because we don't want those to affect then these probabilities for y. So we can do then a test for independence in this scenario where we simply set all those regression parameters equal to 0 for the null hypothesis. The alternative hypothesis is at least some of them are not equal to 0. We could state these hypotheses in terms of models for a reduced versus full model kind of structure, and there you go. To perform a test for independence then with this multinomial regression model, well, let's use a likelihood ratio test. So let's now look at how we can apply these ideas to the fiber cracker data. Our model under the alternative hypothesis of dependence would look like this. Now remember with this data, we restructured it a little bit so that the none category is the baseline category. It was shown as the first column of our contingency table. So because of that then, all of our log odds and how we state our model are going to allow us to do this direct comparison to the none category. Now, we also made a similar change with respect to the x variable, which would be what's actually inside the what's inside the crackers. And so because of that, you don't see the none part here for these indicator variables. And just to make these more meaningful, my indicator variables here, I just simply wrote those in terms of the different levels of the rows. And I guess if I wanted to, I could have changed the subscripts here to be 2, 3, and 4 respectively. Since I'm not using x2, x3, x4, I just decided to leave them as we would normally see them. Okay, so that's our model under the alternative hypothesis. So we can see that depending upon what row I'm in of that table, that's going to affect then these log odds. So let's go ahead and estimate this model. I estimate it in the same way as what we've done before. I use the multinomial function from the nnet package. My response variable is bloat. My explanatory variable is fiber. R automatically creates the indicator variables for us. But one thing that is different here is this weights argument. I need to use weights because of how the data is represented, how the data is represented in the data frame. So here's what the data frame looks like. Notice how I have a column called count. This corresponds to how many people responded a certain way with respect to fiber and gum. So in other words, this row I'm highlighting represents 5 people. And if I wanted to, I could rewrite this whole data set essentially having 5 rows in it to represent this one set of combinations for fiber and bloat. And so basically we need to tell R that, and that's why I have the weights argument. This is very similar to what we saw for a logistic regression model when we had a binomial response format for our data. So I estimate the model. Notice that it says converge there. And so here's then the corresponding estimated regression parameters. So for example, here would be beta hat 2, 1. I have then the corresponding estimated, I have the corresponding standard error. So we have the square root of the estimated variance of beta hat 2, 1 right there. And so the output looks very similar to what we've seen before. To perform the likelihood ratio test, I could use a little ANOVA function. Here I'm going to use the capital ANOVA function. So again, that's in my car package itself. And I put ANOVA mod.fit nom corresponding to where I save my results from the multinomial function. So when I use then the capital ANOVA function, this is what I get. Here's my p-value. Here's my test statistic, -2 log lambda. I have 9 degrees of freedom because I have 4 rows, 4 columns. So 4 minus 1 times 4 minus 1 is 9. Again, there's the p-value. This is exactly the same p-value that we got when we used the assostats function previously from the VCD package. Okay. Now some comments. To examine this potential dependence further that we have here, what one could do is look at odds ratio in a similar manner to what we did for the wheat example. Please see my book for further details about how to do this. Now you'll notice here in this contingency table, in the contingency table and also this data frame here, you see some zeros. Remember how we've talked about how having low cell counts in a contingency table can cause us some issues. And in fact, it actually is doing that here. So if I go back to the corresponding output, notice how we have some extremely large standard errors here. When we did that section on convergence for a logistic regression model, we said, look out for situations where you have extremely large standard errors. That can mean non-convergence. And in fact, that's what it means here. We actually do have non-convergence. If you were to use a more stringent convergence criteria, this will lead to changes in the regression parameters and standard errors corresponding to the high bloating severity row. That's where the large standard errors were coming from. So we have non-convergence. Now you might be wondering, wait a second, why are you using this model then to do this hypothesis test that if we have non-convergence? Well, fortunately, the only part of the model that's actually affected by the non-convergence corresponds to high bloating severity, and this likelihood ratio test actually is not affected by it. Meaning that if I were to use a more stringent criteria, convergence criteria, I'll get exactly the same answer. So in this particular case, it's okay to do that. If, though, you wanted to look at how we can get around having this non-convergence, take a look at my book for an ad hoc solution to the problem. Okay, so that concludes then. Oh, sorry, I have one more small little part here. Excuse me. Now, what if you had, instead of having two variables in your contingency table, or you could say a two-dimensional contingency table where you have rows and columns, what happens if you have 3 variables, 4 variables, or 5 variables? Well, you can put it in this multinomial regression model setting as well. The key is you have, let's say, one response variable, like our bloating severity, and then you treat all the other, let's say, rows, or you could say strata then for a third variable. You could treat those as categorical explanatory variables in your model and represent them in a way in your model to allow you to have independence or dependence between them and the corresponding response variable, and even independence and dependence between them themselves. So for example, suppose you have a model that has a row variable denoted by X, a column variable denoted by Z, where I represent them with these regression parameters. I just put superscript Z letters there to say, okay, this is a beta corresponding to a Z or an X. And what one could do is look at a model like this where you include an interaction term or not include an interaction term between X and Z to understand the dependence between them in a contingency table structure. Okay, so that gives you a little bit of a brief explanation of how to work with a multinomial regression model in a contingency table situation.